Hello, I'm Dr. Fife, and I'm back with section 4.6, which is called Variation of Parameters. So in this brief lecture, we're going to recognize when the method of undetermined coefficients fails and when we have to use variation of parameters. We're going to normalize the differential equation to y double prime plus p of x y prime plus q of x times y equals g of x1 possible. That really just means if you have a coefficient in front of the highest order term, that you divide by it. And then we're going to build the particular solution in the form of u1 y1 plus u2 y2 using Wronskian formulas. And that'll give us a particular solution. Y1 and Y2 are going to be two solutions to the equation, to the homogeneous equation, and that gives you the complementary solution. Okay, so when do we use variation of parameters? We use variation of parameters when the function g of x is not one of the special types handled by the method of undetermined coefficients. So for example, if you have natural log of x, tangent x, or any of those reciprocal trig functions, secant, cosecant, cotangent, any of those, if you have a fraction like 1 over x, or if you have an exponential that contains a higher power, and x squared, you would need to use variation of parameters. So the standard form of the equation that you want it to be written in is where you have that y double prime by itself. So if you have a coefficient, you want to divide by it, and that will tell you what p of x is. P of x is important. And also q of x. P of x is a coefficient of y prime. Q of x is a coefficient of y. Notice here, p of x and q of x are functions of x. So this applies whether you have constant coefficients or whether you have a function of x. So the fundamental set y1, y2 gives you the solutions to the complementary equation, or the solutions to the homogeneous equation. We're going to build the Wronskian y1, y2, y1 prime, y2 prime. If you multiply these, you get y1 times y2 prime, multiply here, minus y2 times y1 prime. That's where this comes from, the Wronskian. We're going to use Wronskians to find our solution. Now we have a couple of formulas. These formulas come from the proof for why variation of parameters works, and this is in section 4.6 in your book. So we're just going to assume, they're all based upon this assumption, that you can write the particular solution as u of 1 times y of 1 plus u2 times y2, where u1 and u2 are functions of x. y1 and y2 are solutions to the complementary. They're the complementary solutions. When you substitute this in to the standard form of the equation, two equations come out. This first one, u1 prime y1 plus u2 prime y2 equals 0. And the second one, u1 prime y1 prime plus u2 prime y2 prime equals g of x. So both of those equations come out, and it gives you a system of equations that you can solve for u1 prime and u2 prime. So it happens that u1 prime is negative y2 times g over w, and u2 prime is y1 times g over w. I usually think of that as u1 prime is w1 over w, and u2 prime is w2 over w, where w1 replaces the first column, the y1 column, with 0 and g of x. And then the second column is going to be y2 and y2 prime. So notice that you're always going to have a 0 here, and 0 times y2 prime cancels, and then you get minus y2 times g. And that's what we have here. Minus y2 times g. That's the same as w1. And then for w2, I think I can fit it here. You replace the y2 column. So I have y1 and y1 prime, and you replace the y2 column with 0 and g of x. And so you're going to get y1 times g minus 0. And there's your y1 times g. So y1 times g, this is the same as w2. So I'll typically use the Wronskians to do it, or w1, w2, and w, rather than the formulas, but either way is fine. Here, once we find u1 prime and u2 prime, we can integrate to solve for u1 and u2. And then once we know what u1 and u2 are, we just substitute it in to get our particular solution. So here, many times when you use variation of parameters, when you substitute in, you're going to have like terms that you'll be able to combine. You want to simplify that particular solution as much as you can. So just a quick overview of the procedure that we're going to use. We're going to find the complementary solution. That's going to give us y1 and y2. We're going to compute the Wronskian, and then we're going to compute u1 prime and u2 prime using, I'm going to use Wronskians, w1 divided by w and w2 divided by w. This will work as long as w is not 0. If w is equal to 0, you need to find a different method to solve. And then once we find u1 and u2 by integration, we'll just substitute it in to get our particular solution, and then our general solution is a complementary plus the particular solutions. So I have one example right here. Y double prime plus y is equal to secant of x. So we're going to start by solving for y sub c. We want to solve y double prime plus y is equal to 0. And I'm going to let y equal e to the mx. When I substitute in, I get a characteristic equation of m squared plus 1 equals 0. So m squared is equal to negative 1, and m is equal to plus or minus I. We get sines and cosines. So our complementary solution is C1 sine x plus C2 cosine x. And we have y1 is sine x and y2 is cosine x. So we're going to let our particular solution be u1 y1 plus u2 y2, where u1 prime is w1 over w, u2 prime is w2 over w. So we have y sub p is u1 y1, y1 is sine x, plus u2 y2, y2 is cosine x, where u1 prime is, well, let's calculate our w's first. Let's calculate w to see if we can even use this method. W has y1 and y2, and then y1 prime and y2 prime. So y1 is sine x, y2 is cosine x. The derivative of sine x is cosine x. Derivative of cosine x is negative sine x. When I calculate those, I get negative sine squared x minus cosine squared x. I can factor out a negative, and that'll give me sine squared x plus cosine squared x, which is our Pythagorean identity. That's equal to 1, and that gives me negative 1. So w is negative 1. And then w1 is replacing the first column with 0 and g. So let's see, what is g? G of x is secant of x. So I have 0 and secant of x, and then my y2 column is cosine x negative sine x. So my 0 times negative sine x is going to be 0, and I'm just going to get minus cosine x times secant x. Now, cosine and secant are reciprocals of each other, and so they'll cancel out to give me 1, and then I have the negative in front to give me negative 1. So w1 is negative 1. w2, I have the y1 column, sine x and cosine x, and the y2 column becomes 0 and secant x. So here, I'm going to get sine x, secant x, minus 0. So that gives me sine x secant x, but secant is the reciprocal of cosine. So I'm going to write that as sine x over cosine x, or tangent of x. So w2 is tangent of x. Okay, so let's see. I have u1, let me change the color there. u1 prime is w1 divided by w. u2 prime is w2 divided by w. w1 is negative 1, w is negative 1, so that gives me 1. u1 prime is 1, So U1 is going to be what I get when I integrate 1 with respect to x. That gives me x. Because this is a particular solution, we don't need the constant of integration. So we'll just leave it as x. So U1 is x. We're going to need that when we write out our particular solution. U1 is x, so I have x sine x. And let's see what U2 prime is. U2 prime is W2 divided by W. W2 is tangent of x divided by -1. That gives me negative tangent x. Maybe I should have left that as negative sine x over cosine x, because that way when I solve for U2, by integrating negative sine x over cosine x, I can let, I don't want to use u because we're using u's up here for u1 and u2. So let's do q equal cosine x. Then dq is the derivative of cosine is negative sine x dx. And that's what I have here. And I can make that substitution then, and I'll get dq over q, which gives me natural log of q plus c. But again, we're not going to use constants of integration. And here q is cosine of x. So I get the natural log of the cosine of x. Okay, so this is my u2. This is my u1. And we have y sub p is, I'm going to copy it from here, is u1 x sine x plus u2, that's natural log cosine x, times cosine x. That's my particular solution. And then my general solution is y equals c1 sine x plus c2 cosine x plus x sine x plus, I'm going to put that cosine x first, cosine x natural log cosine x. And there's our general solution. So the nice thing about variation of parameters is it can be used on any second order ODE. You do have to make sure that the equation is in the standard form, that y double prime does not have a coefficient. If it does, make sure you divide by it. Sometimes when you take antiderivatives, you're not able to come up with nice solutions for them. Watch for domains for like natural logs that come out of the integrals, because you have W1 over W, W2 over W. You might have natural logs, and if you have natural logs, you have limited domains. If W is equal to 0, then you cannot use you can't use this variation of parameters to find the particular solution. And it does not extend really beyond second order. If you were to have a third order equation, the system of equations that comes out would be much more complicated. So this works only for second order ODE. And that's section 4.6. So thanks for sticking with me, and have a great day. Bye-bye.